Concrete is the second most consumed substance on our planet. Only water beats it, and actually water is a major ingredient in concrete anyway. Every year, humanity mines, mixes, and places roughly 3 metric tons of concrete for every person on Earth. It's ubiquitous. Most of us hardly even think about all the concrete around us. We've all seen the gray, lumpy mixture flowing down chutes into formwork to become a road, sidewalk, footing, pile, patio, or foundation. It's easy to think of concrete as a single, uniform substance used around the world, but it's not. The only reason we're able to use so much concrete in construction is that it's cheap. Of the 4 main ingredients, sand, gravel, cement, and water, 2 of them come directly from the ground with little need for processing or refinement. One is water. Cement is the only ingredient that requires a significant manufacturing process, but the raw materials for it are fairly widespread across the globe. Many building materials are constrained by geography. They only grow, occur mineralogically, or are manufactured in specific locations. Then they have to be transported, often at great cost, to where they're needed. It's not true for concrete. No matter where you are on Earth, there's a pretty decent chance that somewhere nearby exists a ready source for at least most of the raw ingredients you need to make it. That simple fact has significantly contributed to its widespread use, but it's done something else too. Take a look at any geologic map. If you're like me, you do this in your spare time anyway. You realize pretty quickly there is tremendous variability in the different kinds of materials that make up the surface of Earth's crust. And the practical result of that, at least for the purposes of this discussion, is that every batch of concrete is just a little bit different, depending on where you go. In a way, that's kind of special, right? In most cases, the concrete you see around you represents a particular place on Earth. Its strength, durability, appearance, and essence are highly local characteristics. It's literally made from materials that were sourced not too far away, but in some cases, we've learned too late that local materials had some hidden problems when used in concrete, and the ways we've worked to fix those problems have created some of the most interesting stories. I'm Grady, and this is Practical Engineering. This is Fontana Dam on the Little Tennessee River in North Carolina. At 150 meters, or nearly 500 feet in height, it's the tallest dam east of the Mississippi River. The north shore of Fontana Reservoir forms the border of Great Smoky Mountains National Park, and if you're through hiking the Appalachian Trail, the famed 2,200-mile path through the wildest parts of the eastern United States, you have to walk right over the top of it. Built by the Tennessee Valley Authority, or TVA, Fontana was completed in 1944 just in time to provide hydropower to the Alcoa aluminum smelting plant at the end of World War II. It's a concrete gravity dam, meaning that it derives its stability to hold back Fontana Reservoir entirely from its own weight. And boy, does it have a lot of weight. More than 2.1 million cubic meters of concrete went into the structure before it was finished. That's well over half the volume of Hoover Dam. And if you watch the same kind of videos I do, you know that putting all that concrete in Hoover Dam was a major challenge. Concrete heats up as it hardens, which can negatively affect the curing process, but more importantly, it causes the concrete to expand. For a structure like a dam, sandwiched between 2 rocky abutments, that expansion can lead compressive stress to build up in the concrete. Then after curing, when the concrete starts to cool back down, it shrinks. That shrinking can lead to cracks, especially in mass concrete structures that heat up and cool down unevenly. And cracks are not ideal for dams. To mitigate this issue, pipes were installed within the concrete at Hoover Dam, and chilled water was continuously circulated during construction to pull heat out of the concrete. The same thing was done when they were building Fontana Dam. In fact, in addition to the cooling lines, the dam was built with deliberate expansion joints that would allow each separate concrete block to cool off and shrink. Once the concrete cured, those joints were grouted to add strength and make the dam watertight. It was a pretty robust and thoughtful plan to avoid the buildup of stress in the structure. Or so they thought. In 1972, engineers inspecting the drainage gallery, a tunnel through the concrete dam used to collect and redirect drainage, noticed unexpected cracks right where the dam curves. Later investigation revealed that the cracks extended through a large part of the structure. At this point, the dam was still less than 30 years old. It shouldn't be deteriorating this quickly, but the cracks were serious enough that something needed to be done. Engineers initially blamed the Tennessee sun. Fontana Dam runs almost perfectly east to west with its broad downstream facing directly south. That means a huge area of concrete is exposed to sunlight for most of the day. The sun heats the concrete, causing it to expand, and over thousands of cycles, cracks are inevitable. The curved section of the dam was most vulnerable. Reaction forces from the abutments align with the axes of the dam. Instead of pure compressive stress, the expansion of concrete created bending stress, a combination of expansion and contraction at the corner. In addition to the cracks, the movement was also causing the spillway gates to bind up. After instruments were installed on the dam, the scope of the problem became clear. Thermal movement is cyclical with the seasons. Concrete may expand in the summer, but it returns to its original size in the winter as temperatures cool. Fontana had some of that, but underneath the cyclical changes was a continuous one. The concrete was permanently growing. TVA took some cores of the concrete to start planning a repair and sent them out for testing. When the results came back, the reason for the unexpected growth was discovered. The laboratory that examined the concrete under the microscope noticed that some of the aggregates inside had dark rims around them. That is a classic sign of alkali-silica reaction, or ASR, sometimes known as concrete cancer. The fundamental components of concrete are aggregates, large and small, bound together by a paste of cement and water. As the cement paste hydrates, potassium and sodium hydroxides dissolve into the water within the tiny pore spaces of the concrete, creating an alkaline solution. In some cases, this is a good thing. The alkaline environment is great for steel reinforcement, helping to prevent rust. But for some types of aggregates, it causes a serious problem. Specifically, if reactive forms of silica are present, they can more readily dissolve in the high pH water, combining with the alkalis to form a kind of gel. As that gel absorbs moisture, it swells and expands, causing internal stress and cracking. This is an extremely widespread problem that's caused structural damage in every state in the US and many countries around the world. You usually don't have to search far for an example of a cracked-up bridge, broken sidewalk, or ruined building foundation that resulted from an alkali-silica reaction in the concrete. Fortunately, the reaction requires 3 conditions, so there are quite a few ways we deal with it. For one, an alkali-silica reaction requires the aggregates to actually contain silica, also known as silicon dioxide. Well, 90% of the Earth's crust is made up of silicate minerals, so this might not seem possible to avoid. Luckily, only certain forms of silica are significantly reactive in concrete. We have tests we can perform ahead of time to identify quarries or sources of rock that react with cement, allowing us to just avoid the issue altogether. But like I mentioned before, the cost of concrete is really sensitive to transportation costs. The farther you have to go to get suitable aggregates, the higher the project's costs rise, so avoiding local materials is not always ideal. The second condition required for an alkali-silica reaction is highly alkaline cement. So we have ways to control for that too. Cement can be manufactured to have lower alkali content, and we can use what are called supplementary cementitious materials, like fly ash, to replace some of the cement in concrete. Those solutions only work if the concrete isn't already in place, though. The third factor of an alkali-silica reaction is excess moisture. You can just keep the concrete dry with waterproof coatings or membranes. Without moisture, the gel can't expand, so the problem is solved. But there are some structures where waterproofing is a pretty big challenge. So TVA was in a bind, literally. They were facing the possibility of just having to perpetually repair cracks and equipment as Fontana continued to expand. Then they decided to get creative. Kristen Smith is the senior program manager for dam safety at TVA, and she explained the thought process.
The impacts on the spillway and the powerhouse equipment, that led to major maintenance and repairs. need to move from the reactive approach. That's not a long-term solution, to a more proactive approach.
The proactive approach they landed on was a fourth option for dealing with ASR. Rather than trying to stop the reaction, TVA decided to just give the concrete more room to grow. The solid rock abutments at each end of the dam had no room to give, so that space would have to be found in the dam itself. In 1976, they embarked on a fairly novel operation to cut a relief slot all the way through Fontana Dam and do it without draining the reservoir or causing any disruptions to the hydropower plant. The idea was pretty simple. Instead of building up axial stress as the concrete expands, the dam can expand into the newly cut slot. Simple in theory, pretty challenging in practice. How do you saw a dam in half? Luckily, TVA has done this at 2 of its other dams in addition to Fontana and shared some footage of that so you could see it happen. These are big dams, so this isn't sawing with blades you find at a hardware store. The tool used for cutting through concrete looks more like a rope than a saw blade.
It is diamond wire, and it's really neat. If you touch it, it's 15 millimeters, which is a little over half an inch. It's abrasive. I mean, it would rub your skin if you drug it across your skin, but you can touch it, you can run your hand along and it's not going to cut you. It can cut through concrete, it can cut through steel. Looks like a big necklace.
That big diamond necklace runs along pulleys strategically installed on the dam to advance the slot downward. The saw pulls the wire in a loop, managing the slack and keeping constant tension against the bottom of the slot. There are a lot of advantages to this in addition to the practically unlimited depth. It causes very little vibration or dust and provides a clean cut without breaking the edges. But there's a pretty obvious challenge of cutting a slot in a dam. How do you deal with the water? Turns out it depends on the dam. At Fontana, Crewe's installed a cofferdam on the upstream face to hold back the reservoir during the operations. It's basically half a steel pipe that seals against the concrete face on the sides and bottom, just big enough for access to adjust the pulleys. At Chickamauga Dam, the geometry made a cofferdam less feasible, so instead they broke the process up into 3 sections separated by boreholes drilled downward into the structure. One section could be cut by the diamond wire while the other borehole was sealed, preventing water from moving through the slot. That's easier said than done, but you can look to your feet for inspiration. The seals installed in the boreholes are long rubber tubes called sock seals.
It's like a sock you put on your foot, but half-inch thick rubber and 100 feet long. And I've heard it described as kind of like an inside-out fire hose. Very strong and waterproof, but to some degree flexible.
The mess is another problem. The dust from the fresh-cut concrete mixes with lubricating water to form a slurry that runs out of the slot. Concrete slurry is not good for the environment. It mucks up the water and changes the chemistry, so the slurry generated by the cutting process has to be captured and pumped to holding tanks. After concrete particles have settled out, the water can be recirculated to control the dust and lubricate the wire as it cuts. And this whole process happens essentially non-stop. Time is of the essence so that the internal stress doesn't close the slot while the wire is still inside it. Slot cutting is relatively low impact on the dam operations, but parts of the dam have to be shut down to avoid an accident, like a broken wire being pulled into a hydro unit or spillway gate. One of the reasons this is possible at all is that TVA's concrete dams experiencing ASR are all gravity dams. In essence, that means that any vertical slice of the dam is theoretically stable on its own without lateral support. Cutting a slot in an arch dam wouldn't work because they depend on axial thrust forces for stability. Before, during, and after the slot cutting operation, there's an intensive monitoring program to keep an eye on how the dam is behaving and methodically measure the movement and strains to make sure the dam responds in the way the engineers predict.
We have hundreds and hundreds of instruments on the concrete portion of the dam. We measure the slot that we've cut. Is it closing? Is it opening? At what rate is it closing or opening? We measure our spillway piers. Are they moving? We measure expansion joints, everything in every direction we measure.
And those measurements are important because the slot cutting isn't a one-time permanent solution. This doesn't slow down the alkali-silica reaction in the concrete at all. It just mitigates the stress building up in the structure as the concrete expands, which is basically a non-stop process. Over time, the slots close. That means that TVA has to go through the operation regularly.
Every approximately 5 years, we use finite element analysis models on our concrete growth projects. So they take all of those years of new information, data from the instruments, and they recalibrate and they rerun these models, and they can tell us how effective the slot cut is. They can tell us when we need to do it again, whatever we need to do to ensure that we are maintaining the integrity of our dams and the adjacent equipment. That's what we do.
I was curious why they don't just cut a big slot to get a longer period of relief before having to do it again. In hindsight, it was kind of a dumb question.
Simple answer, so we don't leave a big hole in the dam. You know, the slot cut at Chickamauga is approximately a half an inch. It's a lot easier to stop water from flowing through a half an inch slot in a dam than it would be maybe a 6-inch wide slot. And in addition, slot cutting is expensive.
In other words, TVA wants to disturb their structures as little as possible while still mitigating the problems ASR causes. It's a back and forth thing. You cut, observe, wait, and only cut again when it's necessary. It's good stewardship of the resources available to take care of the structures we've already built. Alkali-silica reaction in concrete is a huge problem. It's something engineers have to consider when designing basically any concrete structure, which means it's something that quarries, batch plants, testing labs, and contractors have to think about as well. Since the 1970s, we've gotten pretty good at avoiding it in our structures, but since it's often a slow-growing issue, we're still figuring out how to deal with the problems it's causing on the stuff we built before we really had a handle on it. On mass concrete structures like TVA's dams, it could have been a death blow, significantly shortening the lifespans of these massive projects, but they figured out a creative solution to live with it.
I mean, it's cool. And when you think about a dam, it's a water barrier. It is designed to hold back water. So the last thing you expect to do is to cut a piece out of it. But we do. We do.
Reactive aggregates are a hyper-local phenomenon. Go a few miles in any direction and the composition of rocks can completely change. That's true for a lot of parts of life, but one thing I never considered was how specific a sports stadium is to the city it's based in. There are huge differences in how they're built, where they're located within a city, and how it feels to watch a game. One of my favorite channels, Mapify, produced a 3-part video series called Beyond the Bleachers that explores the people, policies, and priorities that shape the differences in stadiums between the US and Europe. And if you want to check it out, it's only available on Nebula. You probably know about Nebula now, even if you're not subscribed. It's a streaming service built by and for independent creators. No studio executives deciding what gets the green light, no advertisements driving the content into a single style. It's just independent creators making the stuff they're excited about with as few barriers and distractions as possible between you and us. My videos go live on Nebula before they come out here, and my practical construction series was specifically produced for Nebula viewers who want to see deeper dives into specific topics. I know there are a lot of streaming platforms out there right now, and no one wants another monthly cost to keep track of, but I also know that if you're watching a show like this to the end, there's a ton of other stuff on Nebula that you're going to enjoy as well. So we've made it dead simple. Click the link below and sign up for a free trial. Watch whatever you want for 3 days, totally free. If you love it, pay just one time. for an entire year's access at go.nebula.tv/practicalengineering. We also have gift cards if you want to get a subscription for someone you love, or you can get a lifetime membership for $200 off right now. Pay once and have access for as long as you and Nebula last. Hopefully that's a long time. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. Thank you for watching, and let me know what you think.